IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Sammy said, if you have questions, please use the Q&A box on the bottom right of your screen to post the question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we are happy to welcome Mohamed Esseghir, research scientist in elastomers, electrical, and telecommunications R&D of the Dow Chemical Company, Collegeville, Pennsylvania, USA. Mohamed will present his paper on enhanced foaming polyolefin insulation for high-performance telecom cable. Mohamed is a research scientist in elastomers, electrical, and telecommunications R&D for the Dow Chemical Company. Mohamed holds a BSc, Bachelor's of Science in Chemical Engineering from the Algerian Petroleum Institute and Master's of Science and PhD in Mechanical and Aerospace Engineering from Rutgers University. Following postdoctoral work at Stevens Institute of Technology, Mohamed joined Union Carbide's polyolefin research team in 1997 and subsequently the Dow Wire and Cable R&D team in 2007. He is currently responsible for new material research for the telecommunications segment. Mohamed holds 14 granted patents and has served as a board member of the Polymer Processing Institute at the New Jersey Institute of Technology. Mohamed, we welcome you to present at today's IWCS webinar series event.
Yes, thank you, Ed, and welcome to all, wherever you are. Good morning, good afternoon, and good evening. It's our pleasure to present this work. And first, I would like to thank IWCS and the webinar team for this opportunity to present our work on foamed insulation for high-performance telecom cable. Let me first introduce our team. Ganguai Sun is in our Shanghai Development Center. Theo Grussens is in Horgen, Switzerland. Chet Kmitch and myself are in our R&D Northeast Technology Center in Collegeville, PA. And all the team is part of the Dow Elastomers and Electrical Telecom group. As a background, and I don't think this is to this audience, probably it's very well known that there is a rapid expansion and upgrade of data center infrastructure to support growing demand for data transmission and storage. We are all hungry for more data at high speed and more of it. And that is really driving the increase in operating frequencies of high category data cables with continuing demand for high signal protection. And of course, it's the insulation requirements also are being demanded to do more. There is a demand for low signal attenuation, which is driving the need for technology for enhanced electrical and mechanical properties of the dielectric material, that is the insulation itself. Physically, there are other methods, but for this particular application, physically formed insulations are typically used, and I will say more about that and the reasons why. Expansion ratios of about 50% and greater are generally used, and what is demanded are fine and uniform cell structure. These are cables which are a very thin wall. Generally, the insulation is under 500 microns, and therefore, if we are forming within a 500 or less microns insulation thickness, you can imagine that the insulation structure has to be accordingly. And more also is the fact that these are produced at very high line speed. This is the extrusion speed at which these cables are made. It's about 15 to 1800 meters per minute, depending on the manufacturer. That has a large demand on the design of the insulation itself from a processing standpoint. And polyethylene has been the material of choice for these telecom cables. It's because of a combination of cost. It's an effective way to insulate, and obviously excellent dielectrical properties, as well as mechanical properties and processing speed. We go to the next slide, which is what is our objective in doing this work and what are the targets. Our objective is to develop an improved high-density polyethylene cellular insulation. Obviously, there are products out there, and we want to improve even further. And this insulation, we would like to have it in a single compound, so customers do not have to blend, eliminate this blending step, and which of course leads to inhomogeneities issues at the cable manufacturing step. So our goal is to deliver a fully formulated, ready-to-use compound and eliminate any potential path for introducing a defect. So in terms of the advantage of the proposed technology, number one, it's ADC-free. ADC stands for azodicarbonamide, or AZO in short, which is a known chemical forming agent, also nucleating agent. And the reason for that is that in Europe specifically, there is a REACH directive where AZO has been put on the list of substances of very high concern. So obviously the industry would like to have a REACH compliant system that would not have this problem. The second is that we would like to have a lower dissipation factor compared to an incumbent high density system for improved electrical properties of the cable itself. Obviously, as I mentioned, this uniformity and the fine cell structure is needed. And because of the speed that these lines run, there need to be a compound that has to process with very good processability. So this line speed imposes some rheological constraints to deliver the processing speed. Why is this important in terms of the dielectric materials influence on the losses? Because what matters really are the losses in the cable itself. I captured here what is affected by the insulation of the dielectric material. Obviously, a lot more goes into a cable design, and a lot more can be done by the design to reduce the losses. But in terms of the dielectric insulation, the first one is the attenuation, which is signal loss. It is influenced by the dielectric insulation itself, its properties, which are the dissipation factor and the dielectric constant primarily. And because the design of the cable imposes a conductor size, conductor separation, that will translate into the thickness of the insulation. So the dielectric materials come through that way as well. The impedance, which is anything that impedes the signal, it is the dielectric constant of the material and also uniform adhesion to the conductor. That's why these constructions, most of the time, are core and shell layers, and this formed insulation will be in between. Internal crosstalk also is affected by the insulation, and it comes through more on the mechanical integrity, because to reduce that, there needs to be twinning, twisting, and these induces radial forces on the insulation, so compressive forces. And if the insulation is not of robust mechanical properties, the foam insulation itself can collapse. So as I mentioned, this is not all. The overall performance of the cable is achieved by a combination of both, right? The non-polymer design parameters, but also the proper selection of the insulation material itself. Just a brief background of why we need to foam. Number one, what foaming means, if we say 50% foaming, that means 50% of something else, which is really the gas that is entrapped in these cells. And generally, the gases that are in the cells have much better dielectric properties, whether it's air, nitrogen, or argon, or carbon dioxide. All of these have better dielectrical properties than the polymer that is used. And so that's why when we form in this graph here, it's a simulated calculation of how the dissipation factor responds. And you can see it's a significant reduction in the dissipation factor by foaming. Here we are presenting the dielectric dissipation factor, but the same goes with the dielectric constant itself. Just a brief background of how the process generally works. It is generally a single screw system. Of course, lines are different. They are tandem lines and so forth. But for a high-level description, what we have is the polymer itself, or the polymer compound that is properly nucleated, that is fed into the extruder, melted and pressurized, and pumped to a high-pressure zone where the gas is injected. This is the foaming gas itself. And then what happens, there is a gas-polymer mixture, and as the material is driven to a high pressure, there is dissolution of the gas in the polymer melt. So you have a homogeneous solution that has the gas, and as the pressure is released at the exit, then the foam expands, and I have pictures to show that. So this is the gas injection process, which is generally used for the topic that we are discussing today. Obviously, there is the chemical foaming approach where the compound is prepared with the chemically foaming agent. That's what CFA stands for. And it decomposes during the melt extrusion step. What happens is, relatively speaking, a high level of the foaming agent is needed. It's easy to implement because it's ready to go. There is no gas injection metering and so forth. However, it's limited to about 45% foaming level. And there is the other issue of this is essentially an impurity. What we are introducing itself, it's an impurity, and when it decomposes, it results in byproducts that are also electrical impurities. So the combination of all of this does affect the electrical properties of the insulation. So for these high-end, much higher requirements on electrical properties, we prefer physical foaming, and that's what the industry generally practices. With physical foaming, one can reach up to 70 and even higher foaming level. Obviously, there are no reaction byproducts, and it's overall a cleaner dielectric system. However, it comes with its own complexity. It's a more complex operation, quite a bit of control that needs to happen. And obviously, it's a process know-how to make this a successful operation. Just to recap on what happens mechanism-wise in this foaming process. So I already described how the evolution of the melt plus gas, the formation of this solution, polymer gas solution, and then with the exit and the rapid depressurization and cooling, what we have is, and of course, the presence of the nucleating agents to enable the bubble growth and stabilization via the cooling process itself. What happens when can get a closed cell structure or an open cell structure or a bimodal structure or multimodal structure? And of course, this is controlled by the rheology of the system that is put into the extruder. And if we go to the next slide, why is this important? The cell structure, that is. Actually, this is work from a completely different field than ours. However, it's quite relevant, and what is shown here is the compressive characteristics of foams. It's a polyethylene foam, and depending on the level or the amount of open cells that are present in this foam, as you can see, the compressive strength is quite drastically affected by the amount of open cells present. and essentially two factors. It's really the open cells and the cell size. And graphically here, the cell size, on the other hand, affects the compressive strength, as you can see. If one has a large cell at the same unit square unit surface or cross-sectional area, larger cells means less supporting ribs or walls of these cells. Smaller cells, you can see there is much more supporting structure overall, and that's what brings about the higher compressive characteristics. So this is, from a mechanical standpoint, the form compressive strength significantly dependent on presence or absence of open cells, and also at a similar density, a smaller cell size would result in a higher number of supporting walls. That means higher compressive strength. From an electrical standpoint, which we should not also forget, open cell structure is prone to moisture ingress. That means undesirable consequences. Of course, moisture is not a dielectric medium, so that would affect the dielectric properties. Also, the manufacturing lines for these telecom cables do have an inline spark fault detection, and the spark fault can apply up to 12 kV continuously at frequencies as high as 2.5 kilohertz. So there is continuous monitoring of the insulation integrity as the cable is being made. So if we have a weakness in the dielectric medium or layer, that could lead to, for whatever reason, contamination, moisture, or breakdown in the dielectric path. That would all result in higher spark fault, and of course the cable is not usable. So why do we come? We come in this space where we have how to make this form. We come from the resin technology side. We come from the nucleating technology side. And of course, we look to the end user or the cable manufacturer, and we work with cable manufacturer on the processing side. We should not forget this is extremely important because equipment is different. Extruders are different in designs, whether it's the heating profile or the screw design or the die tooling and so forth. All of that comes in making this high performance insulation. However, from a material designer standpoint or compound designer, we look at the rheology, we look at the nucleating technology, and of course the resin technology itself. So it's really these three parameters that come together to deliver this high performance material. So what we have done, we produced some formed compositions in which we are using a typical high density based system, which is nucleated properly for gas injection forming. We use that as a control. That's the CHDPE system. And then we use two modified systems, MHDP1, that's modified high density system 1, and modified high density system 2. All of these were prepared via compounding on a twin screw extruder with an 18 millimeter 48 L/D, and with the compounding processing information that is shown here. These were pelletized and dried prior to forming on an extrusion line. We used a single screw extruder, 50 millimeter diameter of 40 L/D, 7.5 kilograms per hour throughput rate. We used the carbon dioxide as blowing agent injected on the extruder, and we used this temperature profile that we are showing. And the extrusion line had a static mixing head in the post-injection section. The electrical properties, we used an Agilent 8753ES analyzer on 50 mil plaques. These are solid plaques, so all data we are showing are on solid plaque. And the frequency is at 2.47 gigahertz. for the dissipation factor and the dielectric constant. The density as standard, it's measured according to ASTM B792, and then the expansion ratio is calculated using the specific gravity of the foam itself versus the unformed material. For the cell structure, we analyze the extruded foam, and we do scanning electron microscopy analysis, and of course we do the image analysis on the electron microscope pictures themselves. So that data is dumped into a jump analyzer, which is a statistical package, and we use a Taki-Kramer type of model. So from an electrical standpoint, the control, it has a typical dissipation factor and dielectric constant of what is common for these systems. The modified system 1 has slightly lower dielectric constant, which is in the positive direction, and the dissipation factor is more or less equivalent to the control. Modified 2 has a dielectric constant slightly lower, however, the dissipation factor was much higher compared to the control. This is the, I'm showing here the extrudate coming out of this forming line. And one observation is that the control system, we can see a transparent region at the die exit, which is indicative of really unformed melt that is coming out of the extruder die. And the forming is delayed, so the forming is delayed post-die. Compared to both the modified systems, comparatively speaking, do show significantly earlier forming, which is really indicative, number one, by the absence of this transparent region, which is polymer melt. And the second is when we measure the extrudate forming angle, the both systems, the modified had about 45 degrees theta angle versus about 15 degrees. That's really 3 times the expansion angle compared to the control system, which is really indicative, qualitatively, right, indicative of improved forming for both modified systems. Obviously, this is not enough. One has to go to the microstructure itself, do the microscopy work, and see if this is real. So these are the microscopy images, SEM pictures. The scale is 1 millimeter that we are showing at the bottom of each image. And what one can see, number one is the qualitatively, there is a reduced number of the large cells in both MD modified systems compared to the control. And also there is a larger number of total cells in both modified systems compared to the control. So when we go to the quantitative analysis via the jump analysis actually of the images that, and this is a compilation of several samples. So what we see in the control system, it's a broader size distribution. Number one, the average mean so cell size is about 250 microns. The total number of cells is about 400. And comparatively speaking, the two modified systems, the average is about 189 microns compared to 252. And in the second modified, it's about 213. For both modified, you can see it's 472 cells and 534 respectively versus about 400 for the control. So what it says, it's a confirmation of what is seen in the images, that this is a higher number of cells and smaller cell size, which is really exactly what we were looking for. If we go a bit deeper in analyzing and comparing the three systems, we can see that and you can see the vertical dots are the number of data points that were taken. So the control has about 250 microns, and the modified system too is different, clearly, because the Turkey-Kramer analysis here shows this circle does not intersect with the control circle. So they are different, but clearly the red one is the much more different. So this is the MHDP1 system is clearly the most different in terms of from a statistical standpoint. So what we see is that these modified compounds showed superior foaming performance versus the typical HDPE system, finer and more uniformly distributed cell structures, and the higher expansion ratio. I think it will come in the next slide. And from the images, we also saw a very smooth extrudate coming out of the line. To summarize the foaming performance itself, so average cell size, both systems show clearly difference from the control. The expansion ratio as well, which is what is important as well. So we have about 73%. So these were all extruded under the same processing conditions. So we are comparing compound differences. So both compounds are showing clearly much higher level of foaming compared to the control. So we have larger cell population, finer cell size on average, and a higher expansion ratio. So in summary, what we have developed is a ready-to-use, fully formulated compound for physically formed data cable insulation, exhibiting the following characteristics. Number one, this is an azo-free system. It exhibits lower loss properties compared to the conventional control. We have also demonstrated that we do generate a more uniform and a finer cell structure, which is necessary for these thin wall constructions. And of course, it should have better compressive strength compared to a system which would produce a larger cell size. And rheological characteristics, these are important. We could not have achieved that if we did not have the proper rheological properties. And I must mention here that we have presentations at IWCS before on this topic. So if you want to refer, you can find that. And also, we have shown that these do extrude quite well in terms of processability of the foam itself. So I thank you for your attention. I am coming to the end of my presentation.
Thank you, Mohamed. At this time, we will ask as many questions from the attendees as time permits. And I will start with the first question. Are there any physical property differences in physically foamed insulation as compared to chemically foamed?
In most cases, the key difference is really the line speed, because it's a pre-homogenized, pre-distributed system that is convenient for usage. I would think the material properties would be dominated by the base resin system used, unless if there is plasticization, and that has been reported in the literature, of the byproducts of the chemical foaming agent that could plasticize the material and may impact the physical properties.
Okay. Next question. Are co-extrusions necessary to provide for a skin layer in foamed insulations to provide for the physical integrity of the insulation? If so, does this slow down line speeds below the 1,500 meters per minute speeds?
No, generally no. The skin and the skin material, which is the core, the inner layer and the outer layer, generally are made of a compound or a polymer that is designed for high speed. We have done skin foam core structures, and we have not seen that's limiting the line speed. It's generally triple head extrusion. So yes, you need more than one extruder because there are two different polymer systems, one to deliver the material that is solid, thin layer, and the other is to deliver the formable compound. So yes, it's not a single extrusion, yes.
Okay. Next, how does physically foamed insulation affect the fire performance ratings of the cable relative to solid insulations?
That's a very interesting question. These are not flame retardant systems. If one wants a flame retardant system, obviously it's a completely different design structure that needs to happen, whether they are jacketed with a flame retardant system. But these compounds, the topic of today, is not a flame retardant system.
Okay. Is the melt flow rate of the physically foamed insulation resins and compounds more sensitive than those used in chemically foamed processes?
I think it's more than the melt flow rate. It's really the entire rheological profile of the compound. We tend to speak of melt flow rate and melt index, but that's only one measure over the entire shear rate that these would see. So I rather not speak of a melt flow rate. I think it is the rheological characteristics of the across the shear rate range.
Okay. Next question. What are the extrusion processing parameters important to this type of material?
Yes, it is obviously the temperature profile of the extruder, and as I mentioned, the people have the user cable makers have different extruder designs, screw design itself, the type of mixer and the hardware, and so we generally work with the end user to optimize the profile to be able to run these. Whether it's optimized for line speed, optimize the temperature profile to make sure that we achieve the proper temperature and pressure to be able to dissolve the gas and so forth. So this is an area that, generally speaking, we work with the user of the product to help them out to develop the optimized profile to make these.
Okay. Next question. Is there any data showing differences in cable performance?
Yeah, this is in development, and so I think we will have the data, but at this point I'm just presenting the early work.
Okay. At this time, I see no more further questions. So thank you, Mohamed, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Mohamed after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 Eastern USA time. Our next scheduled webinar event will be on Friday, June 16th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 65 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 8th through Wednesday, October 11th, 2017, at the Gaylord Palms in Orlando, Florida, USA. In addition, the second annual regional UL and IWCS China 2018 Cable and Connectivity Symposium will take place on Monday, March 19th through Thursday, March 22nd, 2018, at the Pudong International Convention Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.